Hey there, here's another episode of Math with the Black Rat. In this video, I want to talk about a differentiation problem that one of my students showed me. It's not so much to discuss how to do differentiation, but I want to talk about some of the algebra that was involved because it's not obvious and it merits a conversation. Ultimately, this goes into an iteration question, which is an A-level A2 topic. And iteration is a lovely theory to talk about. This video is not going to talk about how iteration works or the methods behind it. I just want to look at the algebra because it caused some growls and head scratching, and I went away and I thought about it, and I talked to some math friends and got their thoughts on it, and it's worth some conversation, so here we go. So the original question looked like this. You've got a function y that equals that icky fraction subtract 4 natural log x. We're told that the domain is strictly positive, x greater than 0, which is reassuring because 1, we don't want to divide by 0, and you can't take the natural log of 0, and even worse, you can't square root negative numbers or take natural logs of negatives, so you darn well better be feeding me positive x's, and that's okay. So the question said, show that the derivative of y with respect to x comes out as this god-awful fraction. And we can do that. You have two choices for how you're going to deal with this thing. Differentiating natural log x is easy. That's going to give me subtract 4 over x. He's okay. It's what are we going to do with that first fraction bit? And you can hit him with the quotient rule, or you can take them apart into two separate power functions and then differentiate. That's my personal preference. Quotient rule isn't my favorite technique, but I do see that we end up in a big glommed together fraction, so there's some sense in thinking that quotient rule is a good way to start hitting this. Okay, so to do the derivative, okay, I'm going to do him by quotient rule and then subtract 4x for his derivative next to it. Off we go. You should write this down because I can't put my whole clipboard on the camera at once. I'm not that technologically advanced here. Okay, so quotient rule. So dy dx, and I'm going to assume that you're fluent in quotient rule, and if you need to pause the video to catch up, please do. I'm just going to keep moving. Okay, so derivative of the top times the bottom minus the top times the derivative of the bottom. Now, 2 root x is 2x to the 1/2, so his derivative is going to be 2 times the half x to the negative 1/2. So that's going to be x to the minus 1/2, which I'm going to write as 1 over root x for the purposes of this problem. I'm sorry if that's really faint. I'll write it bold when I put it in here. I could do it now. This is really make it up as you go along. Sorry. When I'm rich and famous, I'll have a professional videographer to help me do these things. Okay, so if I differentiate 2 root x, that's 2x to the 1/2. That's going to give me x to the minus 1/2, and I'm going to write it as 1 over root x. And the reason I'm going to slap it back into a surd and a fraction is because the format they want me to be in involves surds. So let's see where this takes me. Okay, so derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. Now, if I take 2 root x and square it, 2 root x times 2 root x is going to give me 4x. And subtract his derivative, which is 4 over x. Okay, so pause the video if you need to catch up. That's fine. I'm working quickly. Okay, so I've got two separate fractions here, but I see that their denominators are pretty similar. If I multiply him, top and bottom, by 4, then he'll have the same denominator as my first fraction, and I can combine the numerators. So ultimately, I'm going to subtract 16 from the numerator when I combine them. And When I first did this question, I multiplied out all the brackets. But in hindsight, I think maybe I won't. And my reason for thinking that, let me show you why I'm thinking that. Oops. So I'm going to merge my two fractions and have that subtract 16. So let me just write myself out again. And, you know, being absolutely honest, I'm always honest, except when I'm being dishonest. To be absolutely honest with you, knowing what techniques to use is a huge matter of experience. I've been doing math literally for decades. When you've been doing math for decades, you'll be fluent at A-level as well. It's a matter of exposure, seeing lots of different situations, and just doing an absolute chunk of practice. And that will get you used to the rhythms of the algebra and let you kind of catch a sense of what's going on and where you might want to go with it. Again, this is what they're telling me to aim for, and I've got surds involved, and I've got a root x down in the denominator. So that kind of gives me some hints for how I might start chewing on this sucker. You're not going to go wrong if you multiply out the brackets. Let me show you an observation. Scoot clipboard. Okay, so I've got my fractions combined. That's the subtract 16. Okay, all over 4x. This denominator of 4x is not quite the denominator they're asking me for. He's got a times root x on him. And one fast way I can get myself to a root x on the bottom is to multiply this whole mess by root x over root x. And that's the bump him up into equivalent fractions thing. Multiply the top by the same number, the bottom by the same number. Ultimately, you're multiplying by the number 1 when you do equivalent fractions. Thing divided by thing is the number 1. So when you multiply by the number 1, you don't change the value. But you can write the number 1 in a whole mess of creative ways. And my motivation to do that is because, where's my pens? Oh, my colored pens are behind the camera book stack. I knock everything over. Okay, so my motivation for wanting to do this is because I really, really, really want a 4x root x on the bottom. Now, God knows why I would want to do that, but I'm aiming for what the question is telling me to do, and that's legitimate to be motivated by that. So, if I multiply the bottom, I've got my 4x root x, I'm good to go. And if I multiply the top through by a root x, look what's going to happen. You're going to have that 16 times a root x. That's easy math to do. It also looks like that 16 root x up here. Okay. If I multiply this bit by root x, that's going to interact with the 1 divided by root x. And that's going to zap away to 1 and leave me just with 4x squared plus x. And when I multiply root x by this piece, again, I've got root x times root x, and that's going to give me an entire x. So I'm going to have a 2x times that brackety bit. So let's write it out. So 8x plus 1, 2 root x times root x gives me a 2x. Subtract 4x squared plus x. 1 over root x times root x is the number 1. I suppose I could say times 1, track where that went. Minus 16 root x, and then on the bottom I've got 4x root x. And that's a really fast way to deal with a bunch of stuff at once. How do I know to do that? Experience. How do you know how to do that? I'm telling you, and this is part of your experience of learning the damn stuff. Okay? Again, like I said, if you had multiplied out the brackets first, you'd be in the same boat. You still have pieces to multiply through by root x. I would still do this technique, and that mops things up quite quickly. So from here, I still need to do a little bit of work. I do need to multiply out the brackets now, but maybe you can smell where it's going to go. So that's going to give me 16x squared plus 2x. Subtract 4x squared, subtract x minus 16 root x over my denominator. And there's an x squared term, there's another x squared term. That's going to give me 12x squared. Hooray, that's what I was aiming for. I've got plus 2x, subtract x. That's going to give me an add x. That's 4 terms dealt with. Subtract 16 root x all over 4x root x, and I'm home. That's what they wanted me to get. So that's a little bit of algebra I wanted to talk about, not a huge amount. I want to get into the next part of the question. But here's how you can slap that sucker through quotient rule and end up in the format they want. And I think maybe they aimed for this format because it's relatively tidy. I don't have fractions within fractions. Maybe it's a little nicer to look at x root x instead of writing that as 4x to the 3/2. It's nicer for typesetting, certainly. What it does for you mathematically, I don't know. I didn't write the damn problem. It's largely what you want out of life when you do math. Here our goal is to get to the point where they want us, and it's an A-level exam question, so you're showing off your skills. That's a big part of exam questions. Just show off that you learn things. Okay, you learn things. We can get to there. Shut up, Elizabeth. Okay, quotient rule takes you to there. Before we go to the next bit of the question, I just want to show you another way you could have differentiated this, and this is worth paying attention to because I use the following technique all the dang time. I said at the beginning you can break that up into separate power functions, and I'm going to do that. So I hope you've written this down because I need to turn my paper over. Not like you can't back up the video, but okay, there we go. Why am I waiting for you to write it down? Just pause the video, write that down. Okay, so we're going to differentiate it a different way. Excuse me. So this is what we had, 4x squared plus x over 2 root x minus 4 natural log x. Okay, so this fraction, because I've got one lump on the bottom, I'm not doing funny adding or subtractings in the denominator, it's just one piece in the denominator. I can break the numerator up into two separate pieces like this. 4x squared over 2 root x plus x over 2 root x, and then I have my 4 natural log x tagging along. Okay, and now I am going to do the index thing. So I've got x squared divided by 2x to the 1/2. And that means I subtract indices, and that's going to leave me with 1/2 x to the 3/2. And if you need to pause and think about that, please do. So that's going to give me, oh, whoops, sorry, I had a 4 in there. Beg pardon. That's going to give me 4 over 2, which is just the number 2. I'm going to have 2x to the 3/2. Please tell me you agree with that. Okay, 2x to the 3/2. And here, there's my 1/2. X divided by root x, that's x to the 1, divided by x to the 1/2. You subtract your powers and you're going to get x to the 1/2. Okay, so that's breaking up this fraction into two pieces and then mushing everything into clean old power functions. And this is my preferred technique all over the place because it makes differentiation faster. I don't have to mess around with quotient rule. And if you had asked me to integrate this god-awful mess, I can integrate power functions a lot more easily than I can some hideous fraction. And the technique they would expect you to use at A level is to go from here to here and then integrate. So it's a skill you need. and it's a nice way to show off. Okay, so if you want dy dx from here, I'm just following power rules. So I've got 2 times 3 halves x to the 1/2. Bring the power down, subtract 1, plus a half times bring the power down, subtract 1, and then I know how to differentiate natural log. Now, this does not put me into the fraction format that they want, but I think it's a very clean expression to say that. I think that's a very tidy thing to say. And again, you could slap him into index notation. Why the heck not? 3x to the 1/2 plus 1/4 x to the -1/2 minus 4x to the -1. And I think that's a very tidy thing to say. And if nobody cared about the format of your derivative, I might leave it like that. But that's something you'd have to argue about depending what you're going to do with the dang thing. Okay, blah, blah, blah. The next part of the question, here it is written on a separate sheet just to show you the question. Okay, so the second bit of the question says, okay, so this curve has a minimum turning point. Point P is the minimum turning point, and they drew a picture for you so you could see that you actually had a minimum going on. Okay, and you want to show that the x coordinate of your minimum point is a solution of this expression, and this is going to lead into the iteration in part C. So if you are a minimum turning point, i.e. find a stationary point on the curve, well, stationary points happen where the derivative equals 0. Stationary points, or turning points, happen when your derivative equals 0. So what we need to do is take this, set it equal to 0, and try to shove it around into that format. Or we can take my derivative, set it equal to 0, and mush it around into this format. So that's really what I want to talk about in this video. I know that we're already like 17.5 minutes in, but thank you for sticking with it. Let's go to town. So, fresh sheet of paper, why not? Math takes paper, you gotta have space. So I'm gonna take the derivative in the format they gave me, and if I want that sucker to equal 0, we're looking at, so dy dx equals 0, or stationary points. Okay, so I'll write it nicely now. 0 equals 12x squared plus x minus 16 root x all over 4x root x. Now, the first step everybody is going to take is to multiply both sides by the denominator. So 0 equals 12x squared plus x minus 16 root x. And I lost a paper now. This is what happens when you use lots of paper. The expression that they want us to aim for, you should write this down because I'm going to swap a lot of sheets of paper as we go here. You're writing a clean old x on the left, and then you have another mess involving x on the right. And there's 3 x's we could try to solve for. If I solve for this x, okay, add 16 root x, subtract 12x squared, that's not going to be in the format that they want, so we're not going to be fishing for that x. And we're not going to be fishing for that x either, because if I subtract, well, let's see, if I add this term over, and then divide by 16, and then square everything, well, I don't have, I should write this phrase down, shouldn't I? We're aiming for x equals 4/3 minus root x over 12 to the 2/3. Okay. If I'm trying to fish out this x, I'm going to be dividing by 16, and I'm going to be squaring things. And I guess I'm kind of squaring things, but I'm also taking a cube root here. And I'm certainly not dividing by 16 anywhere. So I don't think that's the x I'm fishing out. I think I'm trying to fish that x out. And what I did is I said, okay, fine. 16 root x minus x equals 12x squared. I'll divide through by 12, reducing, that's 4 root x over 3 minus x over 12 equals x squared, and then just square root that mess. We're told that x is greater than 0, so when I square root, I don't need to throw a plus or minus in. I don't need to do that because I'm told that x is positive. And I don't see anything wrong with what I wrote. And there's nothing wrong with what I wrote, according to my nerdy math friends that I talked to about this. They're like, yep, that's going to be fine. And if you want to do an iteration with him, the iterative methods business, he'll work perfectly fine. Your answer will converge. You're good to go. Ain't nothing wrong with this. But it's not the format that they wanted. So the question is, how the hell did they get this? How the hell did they raise something to the 2/3 power? Where did that come from? So here's the crux of this whole video, 21 minutes in. Thank you for your patience. This is what my math friends did. Okay, so we start from here. 0 equals 12x squared plus x minus 16 root x. And they said, now, what they did was not obvious to me, and it's not something that I necessarily would have thought of to do. How did they know how to think of it? Through their own exposure and experience. Why did I not think of it? Because I've had different exposure and experience. Okay, so what they said is, before we go any further, let's just divide everything through by root x. And I'm like, how the hell do you know how to do that? I'll show you what it looks like, and I'll say some more words. So if you divide everything through by root x, you get 0 equals 12. Well, we kind of do have to go back into index notation. So we've really got 12x squared plus x plus, oops, dang it. This is why I never do math in pen. Minus 16x to the 1/2. So we're dividing by x to the 1/2. So if I divide x squared by x to the 1/2, I'm going to have x to the 3/2. X divided by root x is x to the 1/2, and then 16. So the people I talked to said they were motivated to do that first. Then again, we're solving for this x, and you can start to smell that we're going to get a 2/3 power to undo that index. So from here, all right, if we're isolating this x, I'll add 16 to both sides. I'll subtract x to the 1/2 from both sides. So 16 minus x to the 1/2 equals 12x to the 3/2. I'll divide by 12. 16 over 12, there's my 4/3. Minus x to the 1/2 over 12 equals x to the 3/2. Again, I'm trying to isolate that x on the right, which means if I want to undo a power of 3/2, I'm going to raise everything to the 2/3. So if I raise both sides to the 2/3 power, and now you can smell how it's going to shake out, I get 4/3 minus, and we go back into surd notation because why the hell not, equals x. And there we are. So from this collection of working, this seems like a really natural place to land. And the what the hell step is right here. Why were you motivated to divide through by root x? Why the hell would you do that? And I couldn't understand the motivation until one of my friends said, well, okay, we'll do it in pink. If you had, here's an analogy. What if you had x to the 4th plus x squared plus x equals 0? my friend Colin said, would you not divide everything through by x? Or if you know that x can't be 0, would you not divide everything through by x? And I'm like, well, yeah, I would. And he's like, okay, you're doing the same thing here. He said, you've got an x to the 2, an x to the 1, an x to the 1/2. Why not just divide through by your littlest power of x? That's what we're doing here. We're dividing through by the littlest power of x. And when he said that, it started to click for me. That's where I went, oh, is that your motivation? So let me swap colors here. If you had, where's my blue? If you had an equation that went something like x cubed plus x squared plus x to the 1/4 equals 0, he is our littlest power, so why not divide through by x to the 1/4? X to the 2 3/4. You can work that mixed number out. X to the 1 3/4 plus 1 equals 0. In other words, I'm dividing through by x to the 1/4. And it does kind of tidy it up a bit for some value of tidy. I mean, again, we can sit down and have an argument about what tidy means, but that's the motivation. And I think that's what they did, the people who wrote the exam question, I think that's what they did. I'm willing to bet upwards of 50 pence that they didn't even realize what they were doing. I think they just did it naturally as, well, of course you just do the thing and then you naturally land here. And the reason I suspect that is because my friend Colin was all, this is what you're doing, and he could break it down for me. But my friend Ben was, he sent me a snapshot of his scribblings, and he's like, well, I go from here to here to here to here to here. And I'm like, but Ben, why did you do that? And he's like, oh, I wonder why I did that. So he must have just somehow absorbed this idea in general and never really thought about it. So I imagine that the exam board people had the same line of thinking. And that's a pain in the backside when you're a student and you just haven't been exposed to that yet. Ben must have been exposed as a student and just, absorbed it and got on with it. And Colin probably at some point tripped over it and had to think about it. Or maybe my question forced him to think about it. Yeah, that's what they did, and that's why they landed here for the iterative setup. I think that's interesting. It made me feel better that there was a rhyme and a reason to it, and it is an understandable approach. Whether it's natural to you or not is a different question. Another thing you could have done, as I said to my student afterwards, what you could do is if the question says, show that you can get that expression, well, you could take that and start working backwards. So raise both sides to the 3/2 power. Multiply both sides by 12. Excuse me, my goodness gracious, how rude on a video. Shuffle, 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 and you'll get yourself back to this place, which you would recognize as having set your derivative equal to 0. So you might start from here, get yourself to here, get yourself to here, and then reverse engineer. Here's the damn thing. Then reverse engineer x to the 3/2 equals 4/3 minus root x over 12. I don't know why I put brackets in. Raise both sides to the 3/2 power. Multiply by 12. I multiplied you by 12. Again, don't do math in pen. And your link to get from here to here. How did I do it? I wrote it out for you on, or for my student on my paper. How did I guess I recognize from this step that here I have a plain old 16, but here I have a 16 root x. So again, let's multiply both sides by a root x. And being back and forth with surd versus index notation. That will give you your x squared. You're in business. So I guess you do have to recognize, ooh, that's a plain 16, but I need a 16 root x. Let's just multiply both sides by root x. I think that's reasonable to learn how to do that. So reverse engineering is the thing. If you get stuck and you're like, oh, I don't know what the flip is going on, then start with what they give you and see if you can work backwards. This is half an hour of blah, 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 blah. I wanted to say one last thing because I dragged you through my index notation differentiation. That's you. You need lots of paper and a big desk to do math. Okay, maybe you don't. I do. I need a big desk to do math. Okay, so back to how I took the derivative. So here is the original function. Break it into power functions, then differentiate, and I come down to here if I want to write all in nice index notation. And then if I want to set that sucker equal to 0 to find the stationary points, my stationary points, so 0 equals 3x. You're really patient to get this far. I think Zeke fell asleep. Okay, so set the derivative equal to 0. And you might be tempted to multiply everything by an x. What do I want to do? Where are we ending up? We're trying to get to well, I guess it's not so obvious, is it? I might multiply everything through by an x, so I don't have to look at that 4 over x. That doesn't show up on camera. I don't have to look at that 4 over x bit. So if I multiply everything through by x, I'll have 0 equals 3x to the 3 halves plus a quarter x to the positive half minus 4. And that's going to look an awful lot like what we were aiming for here-ish. There's my 3 halves, and I know I'm going to end up, they want me to end up with something raised to the 2/3 power. So he's the x I'm going to try to isolate. So I'll add 4 to both sides. I'll subtract a quarter x to the 1/2 equals 3x to the 3 halves. And you can see where this is going to go now. Divide by 3. Why is that a 1/4? Did I screw something up? Nope. Nope. Sorry. When I divide by 3, that's going to be a divide by 12. My goodness. Divide everything by 3. A quarter divided by 3 is a 12th. My goodness. You're so much faster than I am. You're probably shouting, for God's sake, Elizabeth, it's 12. It's 12. And then raise both sides to the 2/3 and we're home. So a third friend said, quotient rule, why would you use quotient rule? If you power function this sucker and take your derivatives according to power functions, it kind of falls in your lap for how you're going to get that expression that they want, that 4/3 minus root x over 12 to the 2/3 equals x. And so I feel really, really grouchy with this question still, because if they want you to make the derivative that fat fraction, i.e., please invoke quotient rule, but then they want you to end up with that for your iterative method, I think that's the wrong mix and match. I think if you start from here, you end up with what I wanted it to be, which was the square root business, which was perfectly fine on a page I've now lost. Here. I think if you do quotient rule, I think you naturally end up here. But I think if you differentiate according to power functions, then I think you much more naturally end up in the format that they wanted. So I'm just grouchy, but I hope for your indulged 36 minutes here that it makes it less random, that there is method and thinking behind the steps that were taken, and I hope you've picked up some techniques to use in the future. This is all part of developing your experience and your intuition with this stuff. I'm going to shut up now. Thank you for watching. Please yell if you have any questions, and massive kudos and well done for sticking with all this hairy algebra. Go you. Thanks.